All right there. Hi guys. My name is Wilfrid. Let me just close my door for a sec. My name is Wilfrid. I'm a senior math tutor, and today I'll be covering 12 questions from OneClass. They'll be pretty much covering some mathematics and some algebra. A little bit backstory upon myself. I graduated from master with a major in biochemistry and a minor in mathematics. And lastly, if you have any other problems with your homework or with any mathematics, please send them through OneClass and we'll try to get to them as soon as possible. So let's begin. Okay, so the first question reads, what is the formula for the surface area of a cylinder? So a cylinder, as a junior tutor explains, is a three-dimensional figure with two parallel circular bases. Okay, so the criteria for a cylinder is that, first of all, these circles have to be the same size, so they have to have the same radius. You can't have a cylinder with different circles with different radiuses. And the second part is that they're parallel to each other, and that there is a surface that is encapsulating this area between the two circular bases. So the surface area of a cylinder, if we can think about it, is going to be the area of these two parallel circles, and then the area of this lateral surface that is wrapped around between these two parallel circles. Okay. So if we were to look at it and to split it up, this is what it would look like. So let me try to draw a cylinder for you guys first. So, all right, there's my. Oh, okay. This is going to be really hard. Let me try drawing it. Some sticks first. All right, so this is my cylinder. Sorry for the really ugly drawing here. Okay, so this is my cylinder here. So we can break it up into three different components, okay? So first of all, we're going to have two circles of the same size. So that means that they have the same radius, okay? Secondly, we're going to have the lateral surface, right? So if we unwrap the lateral surface that covers the area or the space between these two parallel circles, we're going to have an actual rectangle, okay? So this is what we're going to have. So we need to calculate the areas of each of these and add them all together, okay? So let's write this down first. So the surface area, I'm going to write SA for short, of a cylinder is going to be the addition of these two circles. So area to area of the circle plus the area of the rectangle, okay? So for the circles, it's kind of easy, right? We know what the area of a circle is pi r squared. So it's going to be 2 pi r squared. All right, so we know what the area of a rectangle is, right? The area of a rectangle is going to be its length times its width. Okay, but we want to be a little bit more specific here, right? How does the length and width relate to the radius of the circles? Okay, so first of all, the width doesn't really relate. The width is the height of the cylinder itself. So the width of this lateral area is going to be the height. So let's write that down here. So h for this. And the length, so we unwrapped it around. But if we wrap it back around, we notice that the length of this rectangle or this lateral area covers the circumference of the circles. Okay, so if we were to unravel it, then we would understand that the length of our rectangle here is actually just the circumference. Okay, which is 2 pi r. All right, or pi times the diameter. Okay, so if we were to add this all together, what would we get? So we have the area of two circles, which is 2 pi r squared, times the area of a rectangle, which is pi r, 2 pi r. Okay, and if we were to factor out 2 pi r, we would get pi r, or just r, plus 1. Oh, I forgot the h. So this should be h. Okay, so this is the surface area of a circle, which is 2 pi r squared plus 2 pi r h, or 2 pi r times r plus h. Okay, so this is the rationale of thinking about this, and you can apply this rationale to other shapes like square pyramids or rectangular prisms. You can just apply this this rationale, break it down into simpler shapes, and calculate the areas for each of those shapes. So this solution is correct. Good work. Cool. All right, let's move along to question number 2. All right, so question number 2 reads, how would the pre-image shown in the figure be reflected across the y-axis? So a reflection maintains the distance of each of these vertices respective to its axes, right? But it just flips it across a specific axis, okay? So technically speaking, right now we're flipping it across the y-axis, but we can totally flip it across the x-axis. We can even flip it across a line. So reflection means that we flip it across the axis that we choose, but we maintain the distances of the vertices respective to its axis. So what does that mean here? Okay, so we see here on our grid, and I'll try to draw out a grid for you guys too, so we have it all set up together. Let me scoot this over here. Okay, so first of all, let me label my triangle here, okay? So we have vertices 2, -2, so this is going to be 2 here. So this is going to be -2 here. We have -4 and 5, and we have 2, 4, we'll have 5 over here. Okay, so our triangle has vertices of 2, -2. So let me just draw our triangle here. 2, -4, and 5, -3. So in between these two. Okay, so this is 5, and this is -2, -4. Okay, so our triangle looks like this. Excuse my badly drawn lines. I'm pretty bad at drawing. All right. Sure. Cool. So what it means to reflect it is that we're going to move it across the y-axis. So we're going to label our axes too. So x and y here. So we're going to reflect this across the y-axis. Okay, but we have to be wary of the fact that we need to keep each of these vertices at the same relative distance. So you see here that this first vertice here is 2 units away from the y-axis and 2 units away from the x-axis. So if we were to reflect it over, we would have to make sure that it's 2 units away from the x-axis and 2 units away from the y-axis. Okay, so since we're only reflecting across the y-axis, we don't need to worry about changing the y-coordinate. We just need to change the x-coordinate here. So the first vertex is going to be here. Okay, let's look at the second one. So the second vertex over here, it's also 2 units away from the y-axis, but it's also 4 units away from the x-axis. But since we're flipping it across the y-axis, we only need to be wary of the fact that it's 2 units away from the y-axis. So we're going to put it here at -2 and -4. Finally, we have our last vertice here, which is at -5. So using the same rationale here, we're going to make sure that it is always 5 units away from the y-axis when we're reflecting it. So this is the reflection of that, and this is the triangle that we have. Okay, so this is how you flip or reflect a image across an axis. Okay, so this is what the junior tutor wrote too. So they described what the pre-image is and what the reflection means, and they noticed that the fact for reflection that we have to make sure our vertices are in relative distance to the axis itself. So they reflected it across the y-axis and made sure that these 2 points were 2 units away from the y-axis, and this point was 5 units away from the y-axis. Okay, so there is a formula for this, which you just negative the axis that you are changing. So for example, okay, so let's say that you wanted to reflect across the y-axis. So if you want to reflect across the y-axis, then you will have to, so if you want to reflect point xy across the y-axis, and let's name it A, then it will be negative xy, right? And we'll do a underscore. Okay, so that's how you reflect across the y-axis. If you were to reflect across the x-axis instead, you will have to be wary of the fact that you have to maintain the distance to the x-axis to be the same. So reflect across the x-axis means that for point B of x equals y, or xy, we have to do a negative y, okay? Excuse me. Okay, so this formula gets a little bit tricky when you're reflecting across a line, but I won't cover that here. But one thing to note when you're reflecting across a line, you have to be sure and wary that all points are the same distance from the line and not from the axis itself. Okay, other than that, I have nothing else to say, and this answer is right, so good job. Your solution is correct. Cool. All right, let's move along to question number 3. All right, so what is a general formula to convert radians to degrees and vice versa? So there are different systems of describing angles, and the two main systems are the degrees and the radian system. Okay, so if we were to have a circle here, and we were to have a line, and this is the radius of the circle itself. If we were to rotate this circle around, it would be a 360-degree angle. So what I mean is that every rotation here has an angle relative to its radius, and if we were to rotate it around and meet back to the original point, that would be 360 degrees. So we have the first one, which is the degree system, which is 360. Okay, so it's 360 degrees. Okay, we also have what we call the radian system, which describes the entire circle in terms of pi. So if you were to revolve this radius around the entire circle and meet back at the original point, you would have 2 pi. Okay, so the conversion formula between degrees to radians is going to be this. Okay, the conversion is 360 degrees divided by 2 pi. So this has units of degrees and this has the units of radians. And if we were to simplify that, that will be 180 degrees over pi. So we can use this formula to help to convert between degrees and radians. Okay, so the junior tutor then provides us some examples, and I'll run through that now. Okay, so the first one is that we're given pi over 2 radians. Okay, and we're going to convert that to degrees, right? So we would multiply it by 180 degrees over pi. Okay, these pi's cancel out, and we get 90 degrees. So now we know that pi over 2 radians is equivalent to 90 degrees. And 90 degrees will be a 90-degree angle from the original radius itself. Okay, what if we were given an angle or a degree? So we have 90 degrees. How will we convert that? Well, we'll just have to flip our conversion here. And if we were to simplify this all together, we'd get pi over 2. Okay, so think of this like you are canceling out your units, right? So this is pi radians. I didn't really write the rad here, but this is pi radians. So you want to cancel out the radians, and you'll know you'll get the right answer if your final answer contains the units that you're looking for. Okay, in this first case here, we wanted to get degrees from radians. So we used a conversion factor properly, and we got our end unit of degrees. Okay, in the second one, we wanted to convert it to radians. So we wanted to cancel out our units of degrees, and we would end up with our unit of radian. So make sure that you always check and make sure that you always have the correct units at the end. This doesn't only apply to degrees and radians. This can apply to a lot of different applications in physics, chemistry, even biochemistry, biology. This is a very basic skill that you need to have, okay? So other than that, the solution is correct, and we can move on. Good work. Okay, cool. Question number 4. All right, so what is the inverse function of f of x, which equals 2x minus 3? So I covered really quickly over the last few lessons what an inverse function does. So I'll just cover that again. So let's say that we have a pool of values x that are defined for function f. And through function f, we know that we get a map of values called f of x, which is our range. Okay, so the inverse function, and the notation for that is f of inverse, takes our range and converts it back to its domain. So it takes our values that are defined by f, and it brings it back to the value that maps to that value, if that makes sense. Okay, so there's a general way of calculating your inverse, and it's by interchanging your x and y and then solving for y. Okay, so let's do it with our example here. Alright, so we have f of x equals 2x minus 3. So we want to find the inverse. So we want to switch our x and y. Our y in this case is f of x, okay? So x equals 2 times f of x minus 3. Okay? So we're going to isolate for f of x here. So we're going to add both sides by 3. So x plus 3 equals 2 f of x minus 3 plus 3. So let's cancel out here. And then we're left with x plus 3 equals 2 times f of x. Okay, and then we want to get rid of this 2, so we're going to divide both sides by 2. And we're left with x plus 3 divided by 2 equals f of, I'm going to change the notation now, inverse x. So now we know that our inverse function is x plus 3 divided by 2, or 1 over 2x plus 3 over 2. So it's also a different line function, and this will take our y values of our original function 2x minus 3 and relate it back to its x value. Okay, cool. So this solution is correct. Good work. All right, moving along to question number 5. All right, so how do you find the prime factorization of 75? So what is a factorization, first of all? So we need to talk about what factors are. So factors are basically numbers that, when multiplied together, will have a product of another number. Okay, so that was explained poorly. Okay, so a factor of a number are the numbers that, when multiplied together, will make that original number. So for example, let me use a general example here. Let's say that we have number a. Okay, so its factors will be a pair of its factors will be c times d, which are just numbers, and we call these factors of a because when multiplied together they produce a. Okay, so let's run through some examples. All right, so the factors of, let's say, 18, right? So obviously one of the factors will be, let me put this in red actually. So let's do the factors of 18. So the factors of 18, obviously one of the pairs of factors will be 1 times 18. So anything times itself will be a pair of factors. Okay, what else is a factor of 18? A factor of 18 is 3 times 6. Okay, and another factor, let's say, is 2 times 9. Okay, so these are some natural number or integer number factors for 18. Okay, so what it means by prime factorization is that we want to find the prime factors of a certain number. And what it means by prime factors is that the factors consist of prime numbers. And prime numbers are another definition that we need to cover here. And prime numbers are basically numbers that cannot consist of any other multiplication other than 1 and itself. So a good example of a prime number is 2, right? So 2 has no other factors except for 1 times 2, right? Another prime number is 3. The only factors that comprise 3 is 1 times 3. Another factor is 5, right? And we can keep going. So these are called prime numbers, and there are a ton of them. A good example of a larger prime number will be 31, right? So there's no other factors that comprise 31 except for 1 and 31. So when they ask us to find the prime factorization of 75, they want us to look for the prime factors of 75. Okay? So let's think about the prime factors of 75 here, okay? And I guess another thing that I need to cover is that factorization doesn't really need to be consisted or to be excluded to pairs. They can be triplets of numbers, it can be quadruplets of numbers. And a good example here is right here with 18. With 2 and 9, we can further break this down to 2 times 3 times 3. This will still make 18, but these are a pair or a triplet of factors that comprise 18. Okay, so in the same way, we're going to try to do that with 75. Okay, so we're going to first of all think of a prime factor of 75. So we're going to do a trial test, and we're going to divide 75 by 5 because we know that 75 is divisible by 5. So that gives us 25 times 3. Okay. All right. So now we know that one of the pairs of factors is 25 and 3. Okay. Now, are these the prime factors of 75? No, because 25 is still divisible, right? It has factors of 1 and 25 and 5 and 5. So we're going to use that, right? So 25 has a prime factorization of 5 and 5. Okay? Are these prime factors? Yes, they are, because the only pairs of factors that comprise 5 is 1 and 5. So we have found our prime factors, which is 5 times 5 times 3. Okay, so this is the prime factorization of 75, which is prime factorization, okay? All right. So these are the prime factorization of 75. Okay, in the same case, in my previous example, the prime factorization of 18 can be characterized by 2 times 3 times 3. So that is another prime factorization. So yeah, that's how you be able to do the prime factorization of a number. Okay. So this solution is correct. Good work. Cool. All right, let's move on to the 6th question. So it's another question about prime factorization. Instead, it's about 54. So let's list out all the factors for 54 first. Okay, let's list out all the pairs of factors. Okay, so we have 54 here. Well, first of all, we have 1 and 54, which doesn't really help because it's redundant to us. We have 2 and 27. Do we have a 3? I do believe we have a 3 here. I think it's 3 and 18. Do we have a 4? No, we don't have a 4, and I think we have a 6. We don't have a 5, so it's 6 and 9. I think that's it. And after that, we revert back. 14, no. Okay, so these are all the pairs of factors. So I'm going to write this all down, okay? So I'm going to exclude 1 and 54, but we have 2 and 27, 3 and 18, and 6 and 9. Okay, let's consider the first one, right? So what are our prime factors here? We have 2, but 27 is not a prime factor. But we can further break that down to be 2 times 3 times 9. So we're getting closer, right? So now we see that we have 2 prime factors, which is 2 and 3, but we still have 9, which is still divisible by 3. So we have 2 times 3 times 3 times 3. And now we have all prime factors here. So this is the prime factorization of 54. Okay, let's check out 3 and 18 here, okay? So we only have one prime factor, but 18 is not a prime factor, right? It's not a prime number. So we can further break this down to be 6 and 3, sure, right? So we have 3 and 3, which are primes, numbers, but we still have 6, which is not a prime number, so we have to keep going. So 6 is divisible by 2, so we can do 2 times 3, so it's 2 times 3 times 3 times 3. Cool. Now you guys notice a pattern here, right? The prime factorization is always going to be the same. Let's try with 6 and 9. So here we don't have any prime numbers here, right? We have 6, which is divisible by 3, which is 3 times 2. And we also have 9, which is divisible by 3, which is 3 times 3. And would you look at that, we also have the same prime numbers for the factorization. And that brings us to an important conclusion. Every number, or not every number, but a number that has factors will always have the same prime factorization. And it's the most reducible you can get to the factors of a number. Okay? You cannot reduce this anymore because you can only divide by the number itself or by 1. And dividing by 1 will produce the same number. Okay? So yeah, so the prime factorization is the most reducible factors of a number. Okay? So the junior tutor, they used the 6 and 9 pairing to find our prime factorization, and then they changed the form to be 3 cubed times 2, which is perfectly valid. So this solution is correct. Good work. All right, let's move on to question number 7. All right, so how do you write 45% as a fraction? Okay, so the relation between percentage and fraction is quite simple. So to write 45% as a fraction, we'll take the integer value of the percent and divide it by 100. Okay, so we'll take 45 and we'll divide it by 100. Okay. And that would equal, if we were to reduce it down, so we can notice here that a common factor between 45 and 100 is 5. So we're going to divide both sides by 5. Or the numerator and the denominator by 5, I should say. And we get 9 and 20. All right, so are there any other common factors between 9 and 20? No, there are not, so we end it here, and this is the fraction for 45%. So to convert from a fraction to a percentage, all we have to do is convert this to decimal form and multiply it by 100 and round to the nearest 100th. Okay? So that is the formula, or the algorithm to converting from percentage to fraction. So from percentage to fraction, you divide by 100 and reduce by taking out the common factor. And to convert from a fraction to a percentage, we want to convert this to decimal form, multiply it by 100, and then round it up to the nearest 100th. Or round it up to the nearest whole number. Okay, so that's how you convert from a percentage to a fraction. If you're converting to a percentage, you don't really need to round up, but in this case, we'll round it up. Okay, so that's how you do it. And so the solution that the junior tutor expressed is correct. So they define what a percentage is, which is a percentage is defined as a part of a whole. So part of 100, which is expressed as a fraction of 100. Okay, so how much do we have of 100 of this? So that's to convert the given percentage, 45%, to a fraction, we need to convert it, put the percentage by 100 to get the fraction of 100, basically. And by doing that, you find the reducible factors, and you end up with 9 over 20. So this solution is correct. Good. Cool. All right, question number 8. All right, so in our second question, we talked about what a reflection is. So we're now going to talk about what a translation is. So the translation is the movement of a object from one place to another. And in this case, when we're talking about Cartesian coordinates or rectangular coordinates, we're moving the vertices of a certain shape or object from one location to another. So from one coordinate to another. Okay, so this could be in the direction of the x-axis. It can be in the direction of the y-axis. It can be in the direction of a line. It can be a direction of a parabola per se. It can be in direction of anything, but that's what a translation is. Okay. So let's label our axes here, and we'll show you an example of what a translation is. So I'm also going to describe what the junior tutor wrote too. So the translation means moving all points of an object to a certain distance, all in the same direction. The object is not altered in any way. And what they mean by altered is that it's not rotated. So rotating means that we're taking the point of the object and rotating it in the clockwise or counterclockwise direction. Reflected means that we're not reflecting it across an axis or a line. And resize means that we're not minimizing it or maximizing it. Okay. So let's use an example. Okay. So first of all, I'm not going to use what the junior tutor wrote, but I'm going to describe his example later. I'm just going to use a simple example of a point. Okay, so we have a point here, 1 and 1. Okay, so if we were to say we're going to translate this 3 units in the positive x direction, then, right, so let's do 3 units in the positive x. Okay, so we're moving it 3 units to the positive x. We're moving it from x equals 1 to x equals 4. So x equals 4 is like here. And this is where we'll move it. Okay, so we're moving it this way. All right, let's do a second example. What if we wanted to move it 4 units in the negative y direction? So this is the positive y direction, and this is the negative y direction. So we're moving it 4 units down. We're going to move it to negative 3. Okay, so we'll have negative 3 around here. Oops, sorry. So it would be right here. And we'll have arrow pointing it 4 units down into the negative y direction. Finally, let's say that we want to move it 2 units in negative x and 3 units positive y. Okay? So if that were the case, then we would move it 2 units in the negative x, so we would move it to negative 2, which is like here. Oh, that's way too far. Like here. So negative 2, and we'll move it 3 units up, which is 4. Okay, so 4 will be like here. And we're moving it in a line. Oh, whoa, that's bad. We're moving it in a line, okay? So that's what it means by moving it in translating it in different directions, okay? So I'll give you guys a general formula. So if we're moving it in the positive x direction, then we're altering the x coordinate, right? So here, we're going to take our points x and y. So let's say that we're moving it 3 units in the positive x, then we're moving it x plus 3, y. Okay? If we're moving it 4 units down, if we have a point x and y, then it'll be x, y minus 4. And finally, if we're moving it in both x and y direction, then we have to alter both x and y coordinate, and we'll get, in this case, x minus 2 and y plus 3. And I noticed that I did something wrong. I considered this to be 0. This should be negative 1 here. So that's my bad. This should be moved like here. Okay. Alright, so let's cover what the junior tutor wrote. So they used the triangles instead, and they also outlined what our pre-image is, which is the original image compared to the image, which is after the transformation. So now they have an object here, which is a triangle with 3 vertices. So all of these vertices have to be moved, right? So they use a general formula that we provided here, but instead they moved it 3 units in the negative x and 9 units in the negative y. So the conversion or the translation will be x minus 3 and y minus 9. So each of these points, 3, 4, 7, 7, 8, and 1, will all have to be applied to this now different formula, a apostrophe or a prime. And that gives them the new vertices of their new image. Okay? So the general tool or the general solution for any of these translations is by recognizing what direction you have to move it in, and then applying a general translation first, and then substituting your coordinates in to find your new vertices. Okay? So this description and definition is correct. Good work. Cool. Alright, let's move along. Alright, so the next question is, what is the square root of 225? Okay, so we can use the aspects of prime factorization to solve the square root of 225, okay? So let's think about the factorization of 225. Okay, so if we were to divide it by 5, we would get 5 and 75, okay? So we see here that 5 is a prime factor, but 75 is not, so we can further break this down. So 75 can be broken down to 25 and 3. Okay, let me just make, okay, I don't think 5 times 75 is 225. 5 times 15. No. Let me just make 4, 5. 45, sorry. Alright, so 45, the factorization of 45 would be 9 and 5. Okay, but we can still further break this down to be 3 and 3. So the prime factorization will be 5 times 5 times 3 times 3. Okay, so let's try to solve this square root now. Okay, so the square root of 225, so we could write in this bracket here, or in the square root bracket, that is the prime factorization of 225, which is 5 times 5 times 3 times 3. Okay, so if we rearrange these, we can get 5 times 3 times 5 times 3. Right? So we just rearrange them. These are still the same numbers and the same front prime factors. Okay? And if we were to simplify these brackets, we get 15 times 15. And 15 times 15, another way we can write that is 15 squared. So that means 15 multiplied by itself. And our rule with square roots is a square root of any square is going to be itself. So we get 15. Okay, so 225 just happened to be what we call the perfect square. So a perfect square is basically any number that is the resultant or the product of a number multiplied by itself. So very common perfect square is 4, right? 2 times 2, 9, 3 times 3. And it'll be very helpful for you guys to memorize the perfect squares all the way up to 16. Because those are very common, and if you are able to memorize those and apply them to your homework problems, you'll be able to do them more efficiently. So this is one of the ways that we can solve square roots, by finding the prime factorizations and then grouping them together in a way that it makes more sense for us. Okay? So this solution is correct, except that they included positive and negative 15, which is strange, because we're not dealing with a variable here, we're dealing with a number. So it's actually, you don't really need the positive and negative 15, because we know that it's 15 within the the number itself. So this solution is almost correct. You do not need to assume the sign of the number as it is stated within the square root already. So the only reason why we consider the positive and negative number is if there's a variable within this bracket. So if this was square root of x squared, then we would have to say, oh, it could be positive or negative. But here we have an integer number that is positive, which is 15. So we don't need to assume it's either positive or negative. All right. So unfortunately, the solution is incorrect. But the junior tutor was almost there. All right. Next. How to simplify the square root of 245? Alright, so this is the same thing. So we're going to try to break it down into factors and think about how we can manipulate it so it's easily solvable. Another thing is that 245 is an imperfect square. So that means that there is no number that multiplied by itself that will produce 245. Okay, so because of that, we'll have to, we know that our final answer will include a prime number within a square root bracket. Okay, so let's think about what are the factors of 245, and the junior tutor gives us one which is 49 and 5. Okay, so let me make sure that's correct. 49 times 5. Let me just do a side here. 49 times 5 is 45 to 45. Yep. Okay. So we have a prime factor of 5 here, but we also have 49, which can be further broken down to 7 and 7. Okay. So we can say 7, 7, that's 5. Okay, so now if we were to write the square root of 245, we can write it as the square roots of 7 times 5. Okay, but we can alternatively write 7 times 7 as 7 squared. And in our previous example, we know that any square root of a squared number will just be itself. And we also need to apply a different rule here, which is that the square root of a times b can be written as the square root of a times the square root of b. So we're going to break this bracket up, and we have the square root of 7 squared times the square root of 5. 5 doesn't have a square root that's a whole number, so we're just going to leave that. And the square root of 7 squared is just 7 times root 5, and we have simplified our square root, which is 7 times root 5. So another thing that we could have done is that we could have wrote, so this is an alternative solution, 245 as 49 times 5. And this is where your knowledge of perfect squares comes in, because you can realize that 49 is just the perfect square of 7. So we can write this as root 7, or we can write this as 7 times root 5. So by having this mental knowledge of the perfect squares, we're able to bypass the step, and we just say, oh, the square root of 49 is 7, so we can just take the 7 out of the bracket, or the square root, and this is what we get. So that's what the junior tutor did. And they also described what the product rule of square roots are, which is right here. So this solution is correct. Good job. All right, let's move on to question number 11. All right, so apply the FOIL method to solve for x plus 3 squared. So the FOIL method is a algorithm to helping us expand to, I guess, these kind of binomial terms, okay? So first of all, I'm going to write x plus 3 as x plus 3 squared as x plus 3 times x plus 3. And this, we're going to use some, I guess, some relational geography here to kind of outline our FOIL algorithm. So FOIL stands for first, outside, inside, and last. Okay, so you don't really need to do it in this order, but it does spell out a word, which is nice. You can do first, last, outside, inside, and no one will hurt you about that. Okay. So what this means is that you want to multiply the first two terms in each bracket, the outside terms in relational terms to each other. So if you were to think of this like they're all relationally distanced from each other, the outside is the lateral terms here, and these are the medial terms or the inside terms. Okay, so when they're saying the outside terms, they're talking about the two outermost terms. When they're talking about the inside terms, they're talking about the two innermost terms. When talking about the last terms, they're talking about these two terms. So I'll draw it out here for you. Okay, so the first terms are going to be x times x. Okay, so it's going to be x times x. The outside terms, so we're going to x times 3, so here. All right, the inside terms, which is going to be 3 times x. And the last terms, which is going to be 3 times 3. Okay. Alright, so that's how you FOIL, and once you have found all the products for each of these, then all you really need to do is multiply them all, to add them all together, and you find the sum of all these terms. Okay, so let's do it with this. Okay, so we have x plus 3 times x plus 3. So let's see the outside terms first, which is x squared plus x plus 3, x times 3, which is 3x, plus 3 times x, which is also 3x, plus 3 times 3, which is 9. So now if we were to simplify this, we will get x squared plus 6x plus 9. So the FOIL methodology is an algorithm in which helps you expand binomial terms. But once you get used to it and once you have enough practice, you don't really need to use this, and you can really just do it by yourself without the helping hand of this. So yeah, that's pretty much it. So the Junior Tutor gives us this whole illustration with everything. So this is an excellent solution to the problem. So this is an excellent solution. Good job. Cool. Finally, let's cover the last question of the day. Alright, so find the range of the function algebraically. So I believe in my fourth question, I talk about the inverse, and I'm going to just redraw this. I'm just going to redraw this diagram here. So we have our x, which is our domain, and we have our f of x. Oh, shoot. We have our y's, and this is related to us by the function f, or in this case they use y, right? So this is our range. So f inverse, also, okay, sorry about this being blue, I didn't mean for that. So f inverse is going to take our y values and bring it back to our domain. So what the inverse does, when I explained it in our question number 4, is that it takes our y values, our f of x, and turns it back to x. And in other terms, it takes the range of our original function and converts it to its domain, and the domain of the original function becomes the range. So now, the domain of the inverse function is going to be the range, and the range, or the domain of the original function, or the range of the inverse function is going to be the domain of the original function. If that makes sense, okay? So a strategy that can be involved to calculating the ranges of original functions is to find the inverse function and then find its domain. Once you find a domain, then it's equal to its range. Another strategy is that you can just look at and evaluate the nature of the function itself and come to a logical standpoint of what the range is. Or you can just graph it out and see where the range lies. Okay, but we're going to use this inverse strategy because it is the most, I guess, it covers, we don't really need to use our rationale, or we don't need a graph, right? So it's kind of the easiest way. Okay, so we have our function here. X plus 5 divided by x minus 2. Okay, so we're going to isolate for x. Okay, so if we're going to isolate for x, then we're going to, first of all, cross multiply. So we're going to multiply both sides by x minus 2. So we get x minus 2 times y equals x plus 5. Okay, if we expand, we get x times y minus 2y equals x plus 5. Okay, so we're going to move this 2y to the other side and move this x to this side. So we get xy minus x equals 2y plus 5. Okay, and then we're going to solve for x. So we're going to factor our x, and we get this. And finally, we isolate, and we get 2y plus 5 divided by y minus 1. Okay, so now we have found the inverse function, which is a function of y that converts it to an x value. Okay, so now we want to solve for the domain of this new inverse function. Okay, so we know that the domain of this inverse function is going to be, so we see that this is a rational function. So that means that most values of x make this function valid or define this function, except for y equals 1. Because when the denominator is 0, then we have an undefined value. Okay, so we notice that the domain of this function is y such that y belongs to all real numbers except for y cannot equal 1. And this is going to be our range. Because like I said, the domain of our inverse function is the range of our original function, and that's what we're trying to find. So this is the range of our function. Range of y equals x plus 5, 5x minus 2 is y such that y belongs to all real numbers except y cannot equal 1. Okay, so that's the range. So, so the solution is correct. Good work. Cool. All right. So that wraps up today's lesson. I covered 12 questions around mathematics. So if you have any other questions or issue with your homework or tests or assignments, please submit them through OneClass and we'll get to them as soon as possible. Other than that, I wish you guys a good night and hope you guys learned something. Bye, guys.